Okay, hello everyone. So we have with us here today Adam Koberinski. Adam received his Bachelor's of Science from the University of Waterloo in 2014, and then he got his MA in 2015 and his PhD in 2019 in Philosophy of Physics from the University of Western Ontario. So then he's worked as a postdoc at the New Directions in Philosophy of Cosmology project from 2019 to 2020 at the University of Waterloo as an SSHRC fellow. That was 2020 to 2022. And then he completed Heinrich Hertz. I don't know if I pronounced that right. Heinrich Hertz. Oh, it's actually much easier. I misread. Hertz, standard unit of physics. Visiting fellowship at the University of Bonn in 2021. So Adam, I believe you're still a visiting postdoc fellow at the University of Pittsburgh Center for Philosophy of Science. Is that true at the moment?
To Western now. Yeah, sorry, that's
Western.
my fault.
Okay.
I might have given you outdated information.
Slightly outdated. Back at Western at the moment. However, recently received a new position as faculty in the philosophy department at Lund University as a global research fellow in joint faculties of humanities and theology. So so it's a very special joint physics and philosophy colloquium we have here today. So I hope you guys enjoy it. And Adam, please take it away.
Thanks. Thank you. So the joy and the challenge of interdisciplinary work, especially to a mixed audience, is what I do is, so this is definitely a project in philosophy, but it's philosophy of a branch of physics that might not be familiar to all philosophers. So I hope I've done an okay job at giving enough background without it being only background. I'll get to that later. I also gave a kind of cheeky title to the talk for those of you who are physicists. This probably looks like a very philosophical sounding title. You'll see that it's a bit tongue-in-cheek. I'm not doing a project in like Kantian metaphysics or something like that, but there is metaphysics involved. So there's a larger project, but the main points of this talk that I want to get across to you are that scientifically informed metaphysics, this is a normative claim, ought to pay attention to the pragmatic elements of using scientific theories. So what is often done is that people look at theories as like static objects and try to interpret what those things say about the world from their mathematical structure. One point I want to take away here is that the pragmatic elements of how we actually apply and use those theories are important. I'll look at effective field theories for this. This leads to a rejection of a standard philosophy of science way of interpreting theories, and in favor of, on the basis of effective field theories, what I'm calling the effective view of theories. I think we should learn from effective field theories that there's a certain way that we should have thought about all theories, past, present, maybe future, unless we get a theory of everything. And then the final point is that the reason people ought to pay attention to the pragmatic elements of using scientific theories is that this is a more productive approach to doing metaphysics. It's a more humble one. I'm not going to claim that I can tell you the fundamental constituents of reality and how they interact and how that gives rise to the world of phenomena. But I also think what I'm going to say will hopefully be less immune to criticism and revision. So it's more humble, but in terms of scope, but hopefully more epistemically secure. And I'm going to do all this talking about effective quantum field theories. So the outline here, first, some background philosophical commitments that I'm not going to argue for, I'm just going to state. Then my methodological approach for giving you sort of metaphysical conclusions from effective field theories. And then once I've done that, I'm going to have to take a step back for the physicists in the audience to give a little bit of background on philosophy of science, for the philosophers in the audience, give a little bit of background on effective field theories. And then I will give you the tentative conclusions that I've got so far. This is still work in progress, so I'm happy with all the conclusions, but it might not be an exhaustive list. So background commitments. First, I think we should do epistemology first metaphysics. I've already kind of said that. And I have a background of looking at scientific theories from a sort of pragmatist view. It's a philosophical tradition. So the contrast with epistemology first metaphysics is ontology first metaphysics. One way of thinking about ontology-first metaphysics is you want to start with what the building blocks are, the ontology, the little entities that exist in the world. Maybe you impose not specific things, but conditions on what those entities must do or look like or be like. And then from that, you sort of build up a system that recovers the world of appearances, sort of using that primitive ontology. An example of this is the references here are in the foundations of quantum mechanics. People like, the philosophical view of a Bohmian approach to quantum mechanics takes this view of what are the building blocks? Well, it's something like classical point particles that obey a guidance equation, and then we work out how you recover the probabilities and statistics of quantum theory from that. What I want to do is sort of diametrically opposed to that. Let's start not even at the level of the theory itself, but the application of the theory to the world empirically. Given that the theory successfully describes some domain of phenomena in the world, what constraints does that impose on an underlying ontology, on what the world must be like given the success of the theory? So that's epistemology first. I'm just making up these terms, so it's not like that's what I mean by epistemology first metaphysics. And I'm doing this from a broadly pragmatist perspective. So pragmatism is a view in philosophy. In philosophy of science, it fell out of favor for about 100 years or so. It's sort of having a comeback in the last 10 or so years. What I mean by this is a form of empiricism, so grounded in the empirical world, that emphasizes the active role of human agency in the practice of science. So science isn't just a static collection of theories. Science is an activity that humans do. We construct theories, we gain knowledge, we run experiments, we compare them. It's an activity rather than a static, abstract entity. For philosophers in the audience, it typically rejects the correspondence view of truth, that our theories, sort of capture an image of the way the world is like, in favor of something like a process or activity-based view of truth, that we theories are true or not in the way that they're used and in the way that we can reason with them and interact with the world. The reason it's come back into favor in the last 10 years or so in philosophy of science is there's been a lot of entrenched debates that have been at a standstill in the philosophy of science and in metaphysics. So the debates on scientific realism, whether our theories, we can believe the things our theories say about the world, or our theories are just instruments for making predictions. Whether we make progress in science or not. These are sort of debates that in the 20th century became, people articulated their views, but nobody really convinced anybody of anything otherwise. You just got better developed positions, and they've kind of been at a standstill. And it seems like taking a step back and reconceptualizing the agreed upon assumptions might be a fruitful way forward. So those are the commitments that I have that I'm not going to argue for. You can ask me about them after. But given those, what does coming up with a metaphysics of effective field theories look like? As I've already said, the key insight here being that interpretation should be grounded in our empirical access to the structures, entities, and quantities posited by a theory. So it's how we use and apply the theory. And what we get from effective field theory, or from any theory if we actually look at its context of application, is that there's only limited domains in which a theory applies. We're not going to get from looking at even what we take to be our most fundamental theories a comprehensive view of everything that exists in the world or anything like that. We're going to get something that's somewhat fallible because the way we connect our theories to the world is through practice-based procedures, and we might think we can extend to new domains and maybe we can't. And so we should be content with what I'm calling regime-dependent truth, so that things are, certain conditions hold within a given domain, they might not hold elsewhere. To a certain degree of approximation, they might not hold exactly. And we do this, so I'll expand on this further in the talk, but what seems kind of forced on us from the historical peculiarities of quantum field theory, namely that we kind of have to treat it as an effective field theory. So that seems like a necessity that's forced on us. It's actually, we can turn that around and make it a feature, not a bug. We actually should have been thinking about all of our theories as effective theories in some way. Once we've been sort of converted to this view, we realize that actually it's quite an attractive position. And so what I'm going to do at the end of the talk is list some features, theoretical features, that are responsible for the empirical success of effective field theories. I'm mostly focusing on particle physics. I think some of the things, there is some relationships to condensed matter theory as well. But I think some of the things will generalize, some of them won't. That's, again, context dependent. And then what I'm going to do is give you some, maybe, if you're, depending on what your views of metaphysics are, like I said, much more humble features that the world must have in order for the effective field theories to be successful. There's a paper that I was inspired by that's looking at a different sort of approach, but it's by Weinberger, Williams, and Woodward, called The Worldly Infrastructure of Causation. What they do in that paper is kind of a similar approach, but think of, given that we can employ causal reasoning successfully in the world, what does that imply about the structure of the world itself? So I'm doing something kind of similar here, but looking at effective field theories rather than causal reasoning. So this is, again, just a summary. I've kind of said this a few times, but the observation I'm starting with, effective field theories seem to be highly successful in helping us learn about the structure of matter across various scales. So condensed matter physics at the sort of micro scales, and then subatomic scales in particle physics. So given that success, and so one thing you could say is that, if you're a strong instrumentalist, is the world could logically be all sorts of ways, and we've just like by accident found some way of systematizing it that really has nothing to do with the way the world actually is. I'm going to reject that skeptical view. I'm going to say there's at least, given that we can successfully use these theories and reason about the world in sort of robust ways, what must the world be approximately like in those domains? And that, oh, yep.
Yeah, so just a question. What do you mean by how the world actually is? What else is there other than, sort of scientific probe of the world? Like, what does it mean?
Yeah, so this is a good question that this is like a big problem in the entrenched debates that I was talking about in scientific realism. Are electrons real? Well, like we have theories that tell us certain things, and we can go measure those properties. But is there like is there really electrons out there? It's often been called like table thumping realism of like there's some sort of background assumption usually at play that like the world really, whether it's easier to articulate if you have sort of religious background views that the creator that created the world, did they follow the rules that we're uncovering when we're doing science? Or are we just finding ways for systematizing a collection of phenomena? Maybe the creator used very different rules, and we've just come up with other rules that seem to approximately work. So this is when metaphysics, it goes beyond the phenomena. You have to, like, are these things really out there? Are they mind independent? Things like that.
Yeah, it seems like it's kind of, you have to have like a religious claim. Other than that, it's just kind of empty. There's nothing to compare to.
So I agree with you on that, but that's there's a lot of philosophical tradition in scientific realism that would say, that claims that we can somehow be confident of the truth of our theories in some way that goes beyond just their matching the phenomena. So the partially tongue-in-cheek thing is, so if you have, for the philosophers in the audience, transcendental conditions are something very strong. Immanuel Kant made lots of transcendental arguments claiming that there are certain necessary conditions for our experience of the world in certain ways, and because we'd experience the world in those certain ways, then we can be certain of the truth of those underlying conditions. He was wrong, it turns out. So famously, he thought, Euclidean spatial structure is a necessary feature of how we come to understand the world. Science has shown that that's not a necessary truth. It's not even a contingent truth of our world. We've learned, at least if general relativity is to be believed, that our spatiotemporal structure is not Euclidean. So really what I mean is something a bit less strict than that. So these are things later called regulative principles. This is in the pragmatist tradition. But that didn't sound as fun on the talk title. And they're close enough. So I think it's a similar sort of argument structure. Given the success of our scientific practices, what can we infer about the structure of the world to some degrees of approximation within some domains of applicability? So not for all time or a God's eye view in these sorts of deep metaphysical ways. These are things that, given the success of effective field theories for understanding the structure of matter, or how matter interacts, they must be they must hold approximately, they must hold to some degree within some domains. They might not hold in other domains. The domains in which we've done particle physics and condensed matter physics, they must hold. Okay, so that's the overall sort of picture. Now I'm going to tell you, so again, for many of the physicists in the audience, you might be like, well, okay, either that sounds obvious, or like, why is this a debate at all? Well, there's a background in the 20th century philosophy of science that still kind of holds sway today, at least implicitly, that I think I need to give you for context for why this is. If you think this view is either uncontroversial or not really saying anything, here's a little bit of background. So within sort of what's considered orthodox philosophy of science, there was sort of two dominant ways of understanding scientific theories that, to me, I'm going to argue that the features they share in common are what I care more about than the differences here, because I'm reacting against both. One early project in 20th century philosophy of science was to try to reformulate theories in a sort of logical, meta-mathematical, rigorous, precise way to make the reasoning structure that's often, as many of you know, you don't necessarily just deduce consequences from your theories. There's a bit more that goes on there. The hope was that if we came up with the right sorts of formalizations of what a scientific theory is and its content, then we could, automate science in this sort of deductive process. As you might, by today's standards, that probably sounds a little silly. I agree. But that sort of, the remnants of that view hold sway still today. So both the syntactic view was that theories are actually just the formal structure. The semantic view was that they were the collection of models that realize that formal structure. But what's important here is that both treat the proper formulation of a theory as some static, abstract entity that has to be formulated to certain standards of mathematical rigor, to be formulated in an axiomatic system or set theory or model theory or something like that. And what it is to interpret a theory, to understand what a theory says about the world, is to provide some sort of link between those formal structures that constitute the theory and the world. So an example of an attempt to do this in general relativity is to say, well, what is general relativity? Well, it is the set of all models of smooth manifold with certain properties, a smooth Lorentzian metric with certain properties, and a corresponding stress energy tensor representing the matter content, such that the Einstein field equations hold. And that just exhausts general relativity on this sort of view. So the theory, what's important is that the theory is identified with the formal structure, and to provide an interpretation to understand what the theory says about the world, it's enough to work with that formal structure and only with that formal structure, and to map that onto the world in some way. So from the properties of the metrics that comprise solutions to GR, you can then infer things about the world. And I mean, there's lots of things you can do there. I'm not saying that's totally wrong. Obviously, formal structures, especially in physics, play a really important role. But there's been lots of pushback. I'm not the first to make this pushback at all. One main criticism is that this sort of approach seems really hard to apply to scientific disciplines that are not heavily mathematized. So this is a physics philosophy colloquium. If you're outside of physics, it might be much harder to formalize your theories in these ways. You might maybe be able to do like predicate logic or something like that, collections of sentences for linguistic theories. But even in heavily, like theories that use a lot of mathematics or disciplines that use a lot of mathematics, if there aren't sort of firm mathematical foundations for that discipline, you still can't do this, because even if you use lots of equations and statistical analysis, you don't have a, here is what the theory is in this sort of formal structure, give me a set of axioms or model theory or something like that, you still can't get off the ground. So this sort of received view that I'm talking about outside of thinking about physical theories has kind of fallen on the wayside, but it still holds a lot of sway, at least implicitly, in philosophy of physics today, despite criticisms by people like Nancy Cartwright, Laura Ritchie, Ian Hacking. I think you could read some of what Allan Franklin has done as well as being critical of this, looking at how experiment is really important to understanding the structure of a scientific discipline, contextual factors, pragmatics, things like that. So what I'm doing fits into these sort of critical approaches, but from a different perspective. But like I said, at least implicitly, this sort of received view still kind of holds in philosophy of physics. And I think I kind of gave you the illustration in general relativity as an example for that reason, because you can capture a lot of things. Like, physical theories are quite formal. Oftentimes they can be given in a set of axioms, not always. But so you might be misled into thinking that that's all or only the important things for understanding what the theory says about the world. And so this sort of approach then, takes those formal structures as exhaustive and says what an interpretation of the theory is just to tell me what a world would be like in which those structures hold exactly. But even in physics, we need more than this to actually connect to the world. How we apply the theory to the world is going to involve a lot of approximation techniques, a lot of modeling of experimental apparatus, modeling how you model external factors that are outside of the theory, acknowledging that you're not including all factors that might be relevant to an experimental setup, et cetera. So I'm going to talk a little bit about those in particular for effective field theories. This is a little bit of a history. So for the philosophers in the audience, this will hopefully provide some context. If you have any familiarity with effective field theories, this should hopefully just be a quick summary. So the one main problem, if you really wanted to hold on to that formal view of what theory structure is, for quantum field theories, at least in particle physics, there is no known so far underlying formal structure of the kind that's required by these accounts. If you can come up with one, there's a Millennium Prize waiting for you. The existence of Yang-Mills theories with mass gaps that follow a certain set of axioms is a Millennium Prize problem. And yet, those quantum field theories that seem to be messy and not amenable to this sort of interpretation also provide our best guide to the most fundamental structures of matter that we know so far, whether that's in condensed matter physics and in particle physics. Even if we find something later on, the success of these theories means that you shouldn't just ignore them. If you're trying to do metaphysics, you want to understand what the structure of the world is like according to science. These theories are our best guides. So this is going to be very schematic for those of you who actually work on effective field theories. I have a short time to give a talk, so I wanted to try to limit the technical features, but sort of a history of why we get to effective field theories, and then a sort of interpretation of effective field theories as a guide as a sort of exemplar of how we should think of science, at least physical theories more generally. So when people first started writing down quantum field theories, relativistic ones, you basically had to do a sort of approximation scheme, a perturbation theory, where you have a sort of free part of the theory which you can solve exactly, and an interacting part of the theory which you can't solve the whole thing exactly. So if the interaction is small, you can treat that interaction as a perturbation to the free theory. That's also not mathematically rigorous. You have to do a bit more. But roughly speaking, then you can calculate observables in the theory, as O's, as a sort of something like a power series expansion in powers of that coupling constant when you're doing a perturbative expansion. But the problem historically that we had is that these perturbative series sort of diverge in two ways. First, the sum over n does not converge. So that might give you some idea of thinking that what we're dealing with are something like asymptotic series, because that's something that's well defined mathematically. But even more problematic for calculation is that individual terms would also diverge. This is the infrared divergences. So you basically, if you tried to calculate, you would just get infinities. Roughly speaking, you can think of this as when you have to do integrals over arbitrarily high momentum with certain terms, you get divergences there. So we needed to figure out, in order to do quantum field theory, we needed to figure out how to tame those in some way. And the process of taming those is called renormalization. So addressing issue 2, we make the integrals finite by regularizing them. The sort of standard way of introducing this, there's other ways, but you can introduce a sort of cutoff energy scale. So on those momentum integrals, you just maybe put an upper limit. We're going to cut off the integral at a large but finite momentum. Then you sort of introduce counter terms into your theory, into your interacting Lagrangian, to sort of remove the dependence on that regulator, that seemingly arbitrary upper limit scale you put in. If you can make the whole theory, and then you take some limit where you then take the cutoff back to infinity. And if you can make the theory predictive while only doing that with a finite number of terms, the theory is renormalizable. And when you do that, for the right sorts of theories, for like QED, quantum electrodynamics, for example, you get really, really accurate predictions. But historically, this seems very mysterious. We just sort of do a bunch of seemingly suspect formal manipulations, and we cancel infinities in some sort of way, and then we get whatever is left over seems to be an accurate prediction. That seems pretty weird. But it worked, and historically this was a guide to constructing theories. We just require that any candidate quantum field theory must be renormalizable. So this really heavily restricts the space of possible quantum field theories. But then you might want to know, well, why does this procedure work? There's some other questions here that I'll get to in a minute. And later developments historically, the renormalization group was really important for this. And what the renormalization group sort of analysis does is give you a reason, a sort of physical interpretation in some sense of what that cutoff is and why it actually doesn't need to be taken to infinity in most cases. So one thing you can do is just assume you have a well-defined quantum field theory for the sake of argument here, and you want to only consider a small range of energy scales that theory can treat. So you put in a cutoff lambda, splitting the fields in your theory into high momentum and low momentum parts. And you want to just sort of get rid of the high momentum parts. You integrate those out, is what that's schematically called often. And then you get formally an expression that looks similar, considering only the low momentum fields, but now your theory has a dependent, so it gets rid of all those high momentum fields, but in its place you now have a dependence on this cutoff parameter, and you might have new terms, new interaction terms for the low momentum fields. You can continue this process over and over, and you can get a sort of, if you take infinitesimal differences, you get a sort of renormalization group equation for how you can integrate successively over lower and lower momentum. And the resulting theory there is called an effective field theory, because it's a theory that's effective within it's not the true theory that you started with, but it's an effective description over a limited range of energy scales. So the effect of cutting off the high energy physics is that you change the coupling parameters. The low energy theory has new coupling parameters, might have new interaction terms, and this is what the process of renormalization, or this is part of the process of what renormalization is. And what you get from this renormalization group sort of approach is that your theory at different energy scales might tell you different things in some way. The coupling parameters might change at different energy scales. The interaction terms that might be negligible at some energy scales become important at other energy scales. But it gives you a way of characterizing what a theory can say over a range of different energies. And inspired by this view, we can say, well, why did we start with a well-defined renormalizable quantum field theory? Couldn't we just always have an effective field theory if we interpret the cutoff in the same sorts of ways? Our current theory the standard model might just be an effective field theory. So what we should really think of it as doing is having an implicit sort of cutoff in there somewhere. And the sort of approach to doing this, which was, Weinberg talks about in a very famous paper called Phenomenological Lagrangians, is if you want to be completely general, you should include all possible interaction terms in your Lagrangian that are consistent with the fields, the field degrees of freedom that you're using in that domain, and the symmetries that you impose in that domain. And so in general, this will be an infinite collection of terms. How do we use a theory that has an infinite collection of terms? Well, it turns out that as long as that cutoff scale is quite high compared to the energy scales you're actually considering when you're using your effective field theory, most of those terms, the non-renormalizable terms, will be irrelevant, which basically means they are, in the limit where the energy you're considering. I'll get to that in a second. So there's only a small set of terms that will remain in that limit, and these are the renormalizable terms. And so answering the question, why does renormalization work? Well, we misunderstood what was going on with our quantum field theories. We should have been interpreting them as effective field theories. And if we start with a full effective field theory with some high energy cutoff and flow down to energy scales much lower, that line break is at a bad spot, but energy scales much less than the cutoff lambda, then what we get is just the renormalizable part left over in the full limit where epsilon over lambda goes to 0. And so for any finite energy scales, as long as epsilon is very small compared to lambda, the renormalizable part will be a very, very good approximation to whatever the full effective field theory says. And so historically what we get is, in order to understand this sort of mysterious process of renormalization, we reinterpret our theories as effective field theories with these sorts of cutoff scales built in. And then what we learn when we learn that the renormalizable part continues to be successful is that the energy scale at which new physics comes in that we've cut off from our effective field theory is sufficiently high that we haven't actually or our measurements are sufficiently coarse that we haven't yet got terms proportional to this epsilon over lambda yet. So that's sort of the effective field theory view is sort of forced on us by this approach. But it also helps us understand some of these other problems. So what is the form of the underlying theory? Like I said, the overall series diverges. We don't have an exact underlying form, so we don't know that. What about the convergence of the series? We know that the series doesn't converge. Either you can sort of prove that it has 0 radius of convergence for most interesting theories. And so what we have is some effective field theory that solves one problem. It doesn't fit in, there's no exact description, but it's an effective field theory anyway. It's only supposed to hold approximately to within a limited range of scales. So maybe these questions still exist and they're still interesting and worth pursuing, but philosophically they're not as problematic once we're onto this effective view of theories. So what we get from effective field theory, so the technical bit and then the bold bit is the sort of general conclusion here. Effective field theories are defined by a generating functional that has an explicit limit to its range of energy momentum scales. So what we get there is that theories are not universal. An effective field theory is not meant to apply to everything, to all ranges of energy. You also get that you have to, in order to actually extract predictions from these effective theories, there's even more layers of approximation techniques. You either put the theory on a lattice, you do perturbation theory, you have to do various forms of extracting predictions in a way that's not getting an exact number because of those issues with not having an exact underlying formulation. So theories are neither universal nor are they exact. But what you also get, which I don't have time to really talk about with the effective field theory view, I kind of gave you a schematic of relating one theory to its effective approach. Insofar as theories can fit into this framework, you get a nice way of sort of relating theories at one energy scale to theories at another energy scale. and you get a nice sort of picture of how these different effective descriptions relate to one another. And so you can say, well, when we get a more fundamental theory, we get a way of relating it to the less fundamental theory, but we should still expect that it's effective in some way too, and so we're just going to keep getting effective theories of some kind. So this is just a slide I used before, but to summarize, the syntactic semantic view still doesn't work here. It doesn't work for EFTs for all these sorts of reasons, our best theories of matter are effective field theories. So rather than trying to change the theory to meet our philosophical standards of theory interpretation, we should change our philosophical standards of theory interpretation to match onto our best theories of matter. And so turning this around, if we should have thought this way about all of our theories all along, the theories, effective field theories, have an explicit domain of applicability, but this is at least implicitly true of all theories we've ever had. They might not have included like a cutoff scale, but no theory we've ever had has actually been an exact universal description of everything in the world. And so, yeah, it's, we have explicit limits on the domain of applicability, and we're not sort of deluding ourselves into thinking that our theories could be exact descriptions that are universally applicable. Okay, so lots of background. Hopefully, hopefully there's a little bit of enough background here. Now I'm going to go over some requirements, or the conditions for the success of effective field theories and what they imply about the world. Probably a bit briefly, I'm running a bit short on time. So one requirement that's really important for understanding effective field theories is a requirement of locality of dynamical interactions. So quantum field theories work by thinking about interactions between fields at a point, or in a region if we're going to be a little bit more precise, but in a local region. It's important for the success of this framework that we have interactions that by contact or coincidence near a point, and the ability to sort of model the effects of the fields that we've gotten rid of in our effective description as a successive series of local interactions of the remaining fields. And so what this implies about the world, for those of you who know a little bit about quantum theory, you might worry about non-locality at a sort of general level. But at least when we're talking about the structure of matter, despite this non-locality or sort of waviness of quantum matter, at least the interactions will still respect approximate locality to some degree of precision within the right sorts of domains. Another important requirement in relativistic quantum field theories is what's called the cluster decomposition principle, which is a bit more technical. But more or less what it says is, as you remove, if you take, you're doing physics over here and you're doing physics over here, in the limit where those go really, really far apart, the results of your experiments completely factor out, so they're independent of one another. This is another surprising feature if you know a little bit about issues in quantum mechanics, because entanglement implies something like non-separability, and so you might worry that fundamentally events are non-separable, but it's non-separability in a way that behaves well with our experimental access. Even if the world is non-separable, the fundamental stuff is non-separable, our empirical access to it behaves as though it's separable in the right sorts of ways. Oh, oops, wrong one. So we have a sort of limit. Non-separability doesn't completely, as Einstein said at one point, thinking about the sort of EPR correlations, doesn't completely undermine our ability to do physics because it's quarantined in the right sorts of ways. If we had complete non-separability, you wouldn't be able to isolate subsystems from one another. So the world must be such that whatever non-separability there is, it is hidden in the right sorts of ways, and that the expectation values of our experiments decouple. Another, well, less of a requirement, sort of an insight from effective field theories, is that symmetry provides a much better guide to the structure of interactions, or the structure of the more fundamental theory, than the actual dynamical interactions do. Symmetries are often preserved across scales in ways that other features are not. Not always, but much more so than you might think. So if we want to know about what, this sort of big metaphysical project of what is the world really like out there, the symmetry structure of our best theories probably provides a better guide than the specific dynamical interactions. Yes?
I guess, I've been thinking about symmetry, and I'm no philosopher, but symmetries of what, I think, right? It's what is the universe or the reality that you demand obey this. And there are symmetries that are obeyed at all scales, like translation invariance or something.
Mm-hmm. Yeah. I think that's a good question. So the symmetries of whatever. So I'm more modest. Whatever the stuff is, the stuff that makes up the matter that we observe, whether it's fields, particles, something like you can fill in your favorite ontology. It's got to obey the right sorts of symmetries. So it's more of a constraint on the ontology than it is an explicit statement of what that ontology is. And so like it depends. So in effective field theories, I mean, there's certain symmetries like translation invariance that you might think encode space-time symmetries. Like that's not a symmetry of the whatever the matter is, but it's a symmetry of space-time, and so the matter in it has to obey that. Other things like gauge symmetries probably are symmetries of whatever the things are that we're treating as quantum fields in our descriptions. So it's going to be context dependent of what the symmetries of what will. I mean, you might be able to give more specific answers in certain cases, but at a general level, just symmetries are a better guide across. If you want to get at the more fundamental stuff from your less fundamental stuff, whatever that is, the symmetries will probably be a better guide. The next two kind of go together, and these are a bit more this is a bit more specific, but it gets into more general concerns. The ability to have a sort of power counting expansion is really essential to effective field theories in order to say, oh, these successive terms we can neglect because they will be suppressed by increasing powers of the cutoff scale. Depends on, like I've given a very schematic way of doing this, but actually coming up with the appropriate power counting scheme in a given situation is not always trivial. But the fact that you can do this is a really important. It seems to apply to everywhere we've been able to successfully use effective field theory so far. And this coupled to a sort of more general principle is that we can do sort of analysis. Reductionism as a physical project in some sense is useful and fruitful, that we can decompose the effects that we observe in a lab into a successive set of simpler terms, and those terms of being in a certain order where we can say this is the dominant term, so we're mostly correct, then we include this subdominant term. And so this allows you to make progress over time. The world doesn't have to be like that. It could have been the case that even if there were a bunch of component effects, they're so entangled and so, well, entangled is probably a bad word here, but they're so connected to one another that we couldn't decompose them cleanly. There is no way of saying this one has this main contribution and this one has a smaller one. And so what these conditions imply about the world is that if we figured out the correct variables and the correct sort of formalization of a theory, so it's in the level of the Lagrangian where you have these additive terms that you can sort of sort in order of importance. This tells us that this reductionism, at least up until now, continues to be a good sort of approach, or analysis is another way of terming this, of decomposing things into their component parts and sorting those parts apart. And to continue on, for those of you who know that analysis and synthesis is like a Newtonian sort of methodology, or what Newton himself kind of considered himself as doing, is that we can then, once we've isolated certain effects, we can find our certain component causes for what we observe. We can go and observe their effects elsewhere in other phenomena. So what makes us certain that we're not just, so this is, if you're an anti-realist and you say, well, if we can just keep adding more parameters to our theory to account for new effects whenever our theory goes wrong? Aren't we just sort of merely curve fitting, right? You know, for any finite number of data points, if you give me enough terms in a polynomial, I can fit those data precisely. But this so that might cast doubt on the analysis part, but the fact that we can then resynthesize and say, well, okay, I've included this subdominant term, it's going to have effects here, here, and here, and here, and then I can go look for those effects, and I can quantitatively measure those effects, and sort of provide independent lines of evidence. The world is such that we, at least in these domains, we have epistemic access and control, so we can go and check for those effects. This also gives you an idea of where effective field theories, I mean, I have broader arguments for this, but at least here that effective field theories may be limited to domains where we have high degrees of empirical access. We might be able to write down effective field theories and create an effective field theory framework in cases where we don't have a lot of empirical access, but it'll be hard to check. If you only have one line of evidence for a given term in your effective field theory, you can be less certain that you're actually getting at something about, accurate about the world, and that you're not just fitting a free parameter to that effect. Yeah, so this is to make sure that we're doing, it might not be a deep metaphysical God's eye view, but at least we're getting some consistent empirical constraints on our theory. So some potentially contested requirements are things like naturalness or the separation of scales. And this depends on the formulation of what you mean by naturalness and separation of scales. In some sense, separation of scales has to hold. You need to have a cutoff that's much higher than the physics you're considering in order to have this effective field theory expansion. But naturalness might not hold in the same sorts of ways. Oh, and this is a different Franklin. This is Alex Franklin, which is somewhat confusing that I'm referencing here. So one reason you might be skeptical of naturalness as being a requirement is that, at least as far as we can tell right now, the standard model has unnatural parameters in it, namely the Higgs mass. But also, I have more to say if you want to ask about this in the Q&A, is that at least in particle physics, this modal robustness that comes from something like naturalness isn't necessary in particle physics. It's necessary for universal behavior in condensed matter systems, where you have many distinct systems that give rise to the same universal phenomena. But the analogy to quantum field theories in particle physics would be like many distinct high energy completions of the standard model giving rise to the same standard model effects. If the Higgs is sensitively coupled to a unique high energy theory, then there's less that's problematic there, because there's presumably only one high energy completion, unless you want to get very unorthodox with your views of completions of the standard model. There's probably only one correct one. But assuming something like naturalness or separation of scales, if you want to take those, is that not only is there locality of interactions in sort of position space that interactions occur at a point, but there's sort of something like a locality of dynamics in energy momentum space as well, that the momentum energy scales are weakly coupled. But yeah, I want to leave a little bit of time for questions. So what we get here, those might, again, if you're wanting deep, sorry for the title of the talk, if you're wanting Kantian transcendental conditions, they're a bit more modest. So there's limitations. I'm not giving you a revelation of what the fundamental entities are or a guarantee of their universality and security across all scales, across all times in the universe. But we get a different type of more epistemically secure results when we acknowledge that these conclusions hold, that those features of the world hold securely to a certain degree of approximation in the domains where effective field theories have been successful. It's not, and it is more substantial than an instrumentalism, because I think what's really important, what we mean when our theories are getting at the world, is not that they've described all phenomena so far, but that we can undergo like counterfactual modal reasoning, like if I were to do X, or if X were different, how would Y be different? And something like that requires a higher degree of confidence that your theory is getting something right about the world. And we get the idea that future theories must respect these features in their appropriate limits, insofar as string theory or whatever theory of quantum gravity gives rise to the standard model in the right sorts of limits. It must also have these features in that limit. Not at the fundamental level necessarily, but in this limit. Okay, so I want to leave time for questions, so I'm just putting these all up here. So quantum field theory sort of forces us to abandon certain norms for theory interpretation that were common in philosophy, but we should have rejected those anyway. We're forced to here, but we should have been rejecting them all along. And effective field theory inspires this more modest approach to scientific realism and theory interpretation. We should reason from the phenomena to the ontology and not the other way around. And then, yeah, I gave you a list of sort of requirements, some of which is that despite the weirdness of quantum theory in general, non-locality is not completely endemic. Non-separability is also not completely endemic. So thanks.
Thank you, Adam. Do we have questions? First.
And this might be opening a huge can of worms. Thank you for the talk, but I am curious what you, what your work would say, if anything, about given the success of effective field theories, if there needs to be an underlying fundamental theory that the effective theory describes for the, or that like the existence of repeated and usefulness of effective theories implies that that probably can be written down, or whether that is actual, or whether that is an ontological assumption that can be dropped.
Mm-hmm. So there's sort of three ways that I can think of that the world could be. I mean, there's plenty more, but like just in this restricted range, there is some underlying theory that's not itself an effective field theory, maybe a final theory of M theory or something like that. That's a theory of everything, and to which our current theories are all effective. Two, it turtles all the way down. It's just you get a new effective field theory that's up to some limited energy scale, and then you get a new effective theory. Or three, like you said, something maybe something completely different that they're just, there isn't, like maybe there's no underlying theory at all. Maybe there's like I don't think this is true of the standard model, for example, but like maybe we get to a theory of quantum gravity and it is itself an effective theory, but we just have no practical or principled hope of ever finding some evidence for anything underlying it. I think regardless of those, the project of trying to interpret effective field theories on their own terms means it won't matter. As long, like, what do our best current theories say about the world? They say X, Y, and Z. They're limited to these energy scales or whatever other regime domains they might be limited to, and we don't know what's beyond. And I think that epistemic humility is something that's I think is an attractive feature, rather than trying to say make bold. I mean, you can make bold claims about what the world is like, but if you want them to be justified, I think you kind of need to be epistemic, like a bit more modest. Yeah.
Other questions?
Yeah, thank you. That was really interesting. I'm wondering why you're resisting the realist kind of moniker. You said a lot of things, like the theory, if it's doing this great job at making these predictions, is telling us something about the way the world is. Mm-hmm. So it seems like you're presupposing that there's like a way the world is. And I'm wondering, what does it mean to you to say that, would you share that with the realists? Or, and then you also said, maybe there is some ultimate final theory. Suppose we had one. Would you then say, okay, never mind, now I'm going to be a realist because I wasn't sure we could get this, but now that we have, okay.
Yeah, so this is, you're right for picking up on this, because I didn't really talk about it in the talk, but I think the world provides some constraints on how we reason about it, but we impose a lot of our own cognitive structures on the world. And so I think there are ways the world is, and there are various ways we could have formulated. I don't think there's a unique way the world is that our theories describe in some way of they're really, like, these are the terms in the Lagrangian. So I think this is why it's sort of depends on who you ask. I'm either, like, I would consider myself a realist, but it's like a pragmatist type view. And I don't think having a fully exact underlying fundamental theory would get rid of those sort of concerns, because, I mean, it would be a great accomplishment in a lot of ways, and we'd learn a lot about the way we conceptualize the world and the fact that the world pushes back in the right sorts of ways. But yeah, I agree with Leo's point of saying, like, what do we mean? What more do we mean than about is there a real way the world is underlying? I think that question is a bit hard to pin down.
Over here first.
Would you be able to clarify requirement 3? Could you go back to that slide for a sec? It's the symmetry one.
Sorry,
Right.
all these, here we go.
Yeah, I guess are you sort of imposing this as like a requirement, or are you saying, because my QED Lagrangian has a U1 symmetry, but I can sort of maybe come up with a different effective theory that no longer has that. Are you sort of saying that for it to be like an EFT, the way you sort of define it, it needs to also have a U1 symmetry, or?
Well, for the successful, so this is in terms of using the effective field theory. Like, you can, I think, so to set up an effective field theory, I mean, in the sort of bottom-up approach of we don't know what the high energy thing is, you sort of pick, okay, what are the right degrees of freedom, what sort of fermion fields, boson fields, whatever, and you impose some set of symmetries. Now so you're free to choose whatever symmetries you want when you do that, but then if you want to apply it to a domain of phenomena, if you've imposed the symmetries that don't match that domain of phenomena, it's not gonna work of the world, right? So it's in the application of the theory to the world. Like, yeah, you're free to choose whatever symmetries you want, but the effective field theories that work in the domains they work in tell us, the fact that they work tells us something about the symmetry structure there, and that symmetry structure, much of it, barring considerations of like spontaneous symmetry breaking or things like that, will tend to be preserved across to whatever the successor might be.
Thank you.
Okay, do we have a few more?
Yeah, thank you for the talk. I maybe wasn't quite understanding in the beginning. You were saying you're sort of rejecting this transcendental, conditions, or the weaker version you were saying, which I just wonder if there are still so I think it makes sense that you can't figure out what a theory of our world is, without looking. We come up with many physical theories that aren't of our world, basically, but we could imagine living in them. But still, there are certain things that all of those have in common. For example, like a causality is an effect there. So you could imagine if you were living in this Cartesian world, you could still do science and make inferences because there's causal structure to the world. So would something like causalities still be like not a transcendental condition, or is that something that is potentially stronger?
I think it's more of a hedge, similar to my answer to Heather's question, is like, I think a transcendental sort of argument is a bit stronger in the sense that it's like, you're giving like, your reasoning to these things must be true, like, because they're like necessary and sufficient conditions for the possibility of us doing things. Like, so if this doesn't directly answer your question, but it kind of goes towards it, like, if you want to be radically skeptical and say, there's actually no, like, causal influence is fundamentally not there. There's like some, like a trickster demon that set up the world in ways that obeys rules that are completely acausal, but to us, so far, it's looked causal. I mean, this is like getting into a bit ridiculous sort of skepticism, but like, I don't think you can get away from those, but even more specifically of this sort of, so far, to the best of our knowledge, to our regimes that we've applied things so far, the world seems to be this way. It's avoiding the like universalizing generalizations that might Yeah, because so like the Kantian examples of are like space must be Euclidean because it forms the possibility of our experience of the world. If you said like to certain degrees of approximation in the environment we find ourselves in, then that probably would have been totally fine, right? And so it's that sort of hedging a little bit.
Right. Yeah. Thank you.
Okay. First of all, thank you, Adam. Very clear, lucid talk. So my question here is more philosophical, as you might expect. So scientific realism, pragmatic scientific realism. So people who I think you've referenced might just come back and say, well, this is just empiricism, especially if you're starting from the empirical phenomena and then reasoning down to ontology. What would you say to those kinds of people?
At a certain level, so this is kind of a similar question. So at a certain level, I think I'm okay with that. Like whatever word you want to use, I think you're getting at features of the world that are not wholly dependent on the ways we conceptualize the world. They're partially dependent on the ways we conceptualize the world, but not whole. Like we can't come up with any theory we want and just have it be true. Like the world pushes back, and we learn features about what that pushback is like.